Hello. In this video we're going to talk about some of the assumptions that are made regarding the data that we're analysing using a linear model, and then we're going to talk about how we can check some of these assumptions using diagnostic plots which we can produce once we've fitted a linear model. So let's have a look at the assumptions that are some of the foundation of the linear model. The linear model makes basically four assumptions about the data that we're analysing. First of all, it assumes that the data are independent. Secondly, it assumes that the errors are normally distributed, and let's just point out that that assumption is that the errors, the residuals left over after the model has been fitted, are normally distributed. The linear model does not make the assumption that the response variable overall is normally distributed. Thirdly, the linear model makes the assumption that the variance is homogeneous across the range of data. So the amount of spread in the data is the same for small values and for large values. And then finally, the linear model makes the assumption that relationships between variables are linear. So if you have a regression, for example, the relationship between your independent and your dependent variable is best described by a straight line and not by a curve. So we've got these four assumptions about the data that go into the linear model. And you've probably seen people talking, or you've heard people talking about the diagnostic plots that you can produce to check these. If you produce a set of diagnostic plots in R, you get something looking like this, and there's a whole bunch of things there, some of them with odd names like normal, QQ and scale location, and it's not immediately obvious what these plots are and what you need to do with them to check these assumptions about your data. There are four diagnostic plots produced by R as a default. We're really only going to think about the first two, the residuals versus fitted values and the normal QQ plot. The other two diagnostic plots are useful and important, but they're not as important as the first two. And in order to keep things as simple as possible, we're just going to look at those first two diagnostic plots. Okay, so let's go through those assumptions in order, and we'll talk about which of those we can check with our diagnostic plots and what it looks like when we've got violations of these assumptions, and what we can see in our diagnostic plots when that happens. So let's start with what's probably the most important one, and the one that you can't check with diagnostic plots, and that's independence of data. What does independence of data mean? Well, formally, independence of data means that the errors of your data points are not correlated with each other. So knowing the error of one data point doesn't tell you anything about the error on another data point. Less formally, what it really means is that each data point should be an independent estimate of whatever it is you're trying to measure. If you're trying to measure an effect, then each data point should be an independent estimate of that effect. And the likelihood of a data point having a particular value should not correlate with the value of any other data point. If that sounds a bit difficult to understand, let me give you an example. Let's say you're doing an experiment with Drosophila, and you've got two vials of flies, and you give one vial a poor quality diet and you give the other vial a good quality diet, and then you measure the weights of your flies. If you see a difference in weights, you can't conclude that that difference is a consequence of the diet that they've been given. And the reason you can't make that conclusion is that it could just as equally be an effect of the vial they were in. If one of those vials was in a particularly good place and one of them was not, let's say one was warmer than the other and one was not, or there are an infinite number of other reasons why there could be a vial effect. So those flies within each vial are not independent estimates of the effect of diet. If you wanted to do this experiment properly, you'd need to rear individual flies in separate vials on your two different diets and weigh them, or you'd need to use multiple vials and take the vial effects into account in your analysis somehow. Some other examples of ways that data cannot be independent are if you have plants from the same plot. So if you have one plot with fertilizer X and a second plot with fertilizer Y, and you measure how much the plants grow, you don't know if that's a plot effect or a fertilizer effect. And there are lots of other examples. So children from the same school, for example, if you're investigating different teaching methods, then there might well be a school effect, which means that children from the same school would not be independent estimates of how good your teaching intervention is. So independence of data is a really important assumption that we make. It's not something that you can actually test post hoc. It's a matter of experimental design. There's no test you can do on your data to say, are these data independent? Independence is a matter of experimental design. It's much better to think about it before you start doing your experiment than after you start doing your experiment. Lots of people make errors when they're doing science with independence of data. And if your data are not independent, that can really invalidate your entire experiment. There are some forms of non-independence that we can deal with statistically, but there are other forms of independence that we cannot deal with statistically. And if you have serious non-independence in your data, that can really ruin your whole day, your week, or even your whole PhD. So think about independence of data before you do your study or your experiment. You can't fix it if it's not right afterwards. Okay, next assumption, normal errors. So here are some data, and I've fitted a linear model to them, in this case a simple linear regression, and I've drawn a line from each data point to the fitted value, the predicted value from the linear regression for each data point. And those lines represent the differences between the data points and our predicted values from the model, or the fitted values. And those distances between the data points and the fitted values are called the residuals. So some of them are negative, some of them are positive, and you can calculate a residual for every data point in your data set. We often call those residuals the errors because they represent the information that we can't explain, the variance that we can't explain in the data we're trying to analyze. And the assumption behind the linear model that people get hung up on an awful lot is that those errors, those residuals, should be normally distributed. Just to make it 100% clear, the assumption is not that the overall data variable should be normally distributed. If anyone tells you that you should test your data for normality before you do any analysis, that is flat wrong. It's the residuals that we assume are normal. So how can we check whether our residuals are normally distributed? Well, the way we can do it with a diagnostic plot is using something called a quantile-quantile plot, or a QQ plot. This is the standard quantile-quantile plot that R gives you. It's actually the second diagnostic plot that you get when you run plot on a linear model in R, but we're going to talk about it first. If you're not familiar with it, it looks quite weird and you can't immediately work out what's going on. If you are familiar with it, it's a very useful and sensitive way of looking at the distribution of your data. So let's just run through what this plot is actually showing us, and hopefully you'll then be able to see what it is that the QQ plot can tell us. So the y-axis is the residuals from your linear model. They've just been standardized, which means they've been converted to a distribution with a standard deviation of 1 and a mean of 0. But you can think of that y-axis effectively as just being the residuals from your model. And then the x-axis, which it calls the theoretical quantiles, these are best thought of as being the values that those residuals would be expected to have if those residuals were actually drawn from a normal distribution. So if the residuals were drawn from a normal distribution, on average, we'd expect them to have the values that are plotted on the x-axis. They won't have those values every time, but if we did it 1,000,000 times, then we would find that the average value for the residuals would be the same as those theoretical quantiles we've plotted on the x-axis. So we've got the expected values if they are from a normal distribution on the x-axis. We've got the actual values on the y-axis. We've got a line that R has drawn across our plot, and that's the line of unity. So that's the line where y equals x. And if our residuals were actually drawn from a normal distribution, we would expect that those data points should lie approximately on that line of unity. You can see here in this plot that some of them don't. So this one here is an example where the residual is much larger than we would expect. And this one down here is an example where the residual is closer to 0 than expected. So we can look at this plot and we can see whether our residuals approximate to a normal distribution or if they don't. And if they don't, it can tell us how they deviate from that normal distribution. QQ plots are best understood by looking at examples. So what we're going to do now is we're going to run through a bunch of examples of QQ plots showing residuals with different distributions. So let's kick off with some QQ plots with residuals which are actually drawn from normal distributions. These three plots all show you QQ plots of residuals that were drawn from normal distributions. You can see that most of these points are pretty close to that straight line. Some of them are deviating from the straight line a bit. Most of them are fairly close. The main thing to notice is there's no systematic deviation from that straight line. So you don't have all the high values differing from the straight line or all the low values or anything like that. So if you see something like this, that's a perfectly reasonable QQ plot. You don't need to worry about that. The thing to look for is systematic and strong deviation from the QQ plot. Okay, here's another example, and this looks a lot like the one that we were looking at a couple of slides ago. And this is a QQ plot where there is very clearly some systematic deviation from that line of unity. In fact, you can hardly see the line of unity because it's so far down on the graph. And this is an example of where you have positive skew in your residuals. So here is a histogram of those residuals, and you can see that they have very strong positive skew. And let's just talk through what it is about positive skew that gives us this particular shape of the QQ plot. And the best way to think about this is to think about, well, what would it look like if these residuals were actually normally distributed? So here's my attempt at a bell-shaped curve, which is approximately the distribution that these residuals would have if they were normally distributed. And one thing you can see is that we've got a lot of residuals with much higher values than we would expect if our residuals were normally distributed. So this is a positively skewed distribution. We've got that long tail heading off towards high values, and that gives us higher values for the large residuals than we would expect. And those residuals correspond to these points on our QQ plot. And then if we look at the other end of the distribution, where we've got some negative residuals, you can see that we're actually missing a whole bunch of negative residuals that we'd expect to see if our residuals were normally distributed. And in fact, the residuals that we do have towards the lower end of the distribution have higher values than we would expect. So they are closer to zero than you would expect if these residuals were normally distributed. So these residuals, which are closer to zero than expected, correspond to these points on our QQ plot. So when you get a shape like this on a QQ plot, this kind of concave shape, that's a very good indicator that you've got positively skewed residuals. This is a very strong example of positive skew in your residuals, although not something that's unlikely with biological data. This is very common with biological data. Here's an example of a QQ plot showing skew that's rather less strong, but it's still there. You can see that concave shape in those residuals on the QQ plot. And here's our histogram showing you the skew in these residuals, which is still there, although rather less than it was in the previous plot. Okay, here's another QQ plot. This one looks a bit like the ones we were just looking at, only it's the other way round. So our high values of residuals and our low values of residuals both have values that are smaller or further from zero than we would expect. Both have values that are lower than we would expect. And this is in fact an example where you have negative skew in the residuals. This is rarer than positive skew in the residuals, at least in biological data, but you might still see it on occasion. And if we draw, well, again, something that approximates, roughly speaking, to a normal distribution on our frequency histogram here, once again we can see how this distribution of residuals leads to this shape of the QQ plot. So down here we've got values that are more negative than expected. So this is negative skew. We've got a long tail going off towards the negative end of the histogram. And these values that are more negative than expected correspond to these values on the QQ plot. And then when we look at the more positive values, once again we're missing a whole bunch of residuals that would be there if they were normally distributed, and the ones that we've got have values that are closer to zero than we would expect if our residuals were normally distributed. So this is what you see for a QQ plot with negatively skewed data. And you can see that we can draw a kind of convex line through that. And then here's one further example. So QQ plots don't just show you if your data are skewed, they can show you other things about the shape of your data that are often hard to spot if you're looking at a frequency histogram. So this QQ plot here has high value and low value residuals that are further from zero than we would expect. So the high value positive residuals have got higher values than we would expect, and the low value negative residuals have got lower values than we would expect. The residuals in the middle all look about okay. So what's going on here? Well, the answer is this is telling us that although our frequency distribution of residuals is symmetrical, it's not really a normal distribution. And in this case, we've got something called kurtosis, which means that the distribution is pointier in the middle and has wider shoulders than we would expect from a normal distribution. So the more negative and the more positive values of these residuals are larger or smaller than we would expect. And that's because the shoulders of the distribution are more spread out than we would expect if the data were normally distributed. So using QQ plots can show you, it can show you things that you can see reasonably easily in a histogram, like strong positive skew, but it can also show you things that are more subtle and much harder to spot in a histogram, like kurtosis in your distribution of errors. Kurtosis is often not something that you need to worry too much about. It's very common in biological data. Because kurtotic distributions are still symmetrical, it's less likely to have a strong impact on your analysis than skew. But if you've got strong kurtosis in your residuals, you should probably think about whether that might be affecting the outcome of your analysis or not. Okay, the third assumption that we make for our linear model is homogeneity of variance. And what this means is that the variance for your data should be roughly equal whether you're dealing with small values or large values of your response variable. So here's one example. Again, this is with a continuous explanatory variable. And you can see in this example, which is fake data that I made up, that the amount of spread, the amount of dispersion in these data is pretty much the same whether you're dealing with a small value of your explanatory variable or whether you're dealing with a large value for your explanatory variable. And the way that we check for homogeneity of variance in linear modelling is we look at the first diagnostic plot that R gives you, which is the plot of residuals on the y-axis versus fitted values on the x-axis. So once again, we're plotting our residuals, but this time, rather than the expected values of those residuals if they were normally distributed, what we're plotting is the fitted values, and those fitted values are the predicted, in this case, are the predicted values from that linear regression. And here you can see from the graph that there's very little change in the variance as the fitted values increase. And you can see, if you look at the residuals versus fitted values plot, that there's no pattern there in the residuals. The zero value is nicely down the middle of the graph, and there's no obvious change in the way those residuals are spread across the residuals versus fitted values plot. The red line across the middle is a non-parametric smoother that R puts there for you. It's sometimes useful, particularly when you have non-linear relationships, which we'll see in a little while. Don't pay too much attention to it. It's just there as a help to let you understand what the general trends in your residuals are. So that's what your residuals versus fitted values plot looks like when you're dealing with made-up data with really constant variance across the data set. Of course, real biological data never looks like that. Quite often it looks very different, and this is something that you see quite often. And you can see in this case that our response variable has a variance which is increasing a great deal with the values of our explanatory variable. So down at the bottom end of the values of our explanatory variable, we've only got a very small amount of variance, but as the explanatory variable gets bigger, so the amount of variance in the data gets bigger. This is what the residuals versus fitted values plot looks like for that. And you can see that this really strongly reflects that pattern that we can see in the data there. You can see that there's a kind of wedge shape in the residuals, because as the fitted values get bigger, the variance gets bigger. So you can look at that and you can say to me, well, I can just look at the plot of the data and I can see that. And yes, you're right. But you can't always see it when you've got this kind of what we call heteroskedasticity, which means that the variance is not the same across the data set. Sometimes, particularly when you're fitting more complex models, you can't actually see the heteroskedasticity because it's obscured by other patterns in the data. But when you plot the residuals versus fitted values plot, you can see it there. So this is a better way of looking for changes in the variance across the data set than just plotting the data out and looking at it. Although plotting the data out and looking at it is something that you should always be doing anyway. And if you see something like that, that's going to be giving you a big clue that there might be an issue with your data. Okay, here's another example. And this is an example where the linear model we're fitting is an ANOVA rather than a linear regression. So we've got a response variable called y2 in this case, and we've got a factor with 4 levels. And if you look at this box plot, you can see that the amount of dispersion in these data is higher for the C and D levels of our factor than it is for the A and B levels. And if we plot our residuals versus fitted values plot, it looks a bit different. And the reason it looks different is that we only have 4 fitted values. Those fitted values are the means for factor A, B, C and D. But you can see that we have that wedge shape once again. So as the fitted values get bigger, the amount of variance in the data gets bigger. And this again is a fairly common pattern that you see in biological data an awful lot of the time. Okay, the final assumption that we make with linear modelling is linearity, and that means that the relationships between our explanatory variables and our response variables are linear. They come in straight line relationships. Obviously, sometimes we're going to get curved relationships between response variables and explanatory variables. So here's an example of that. I've plotted a response variable and an explanatory variable on the left, and you can see that the straight line we've put through it doesn't really do a great job of describing what's going on. And the reason it doesn't is that the relationship is actually slightly curved. When we plot our residuals versus fitted values plot, as we've done on the right, that slight curve is really exaggerated. So curved relationships really show up strongly in residuals versus fitted values plots. Sometimes when you can't see it even on a simple scatter plot like this, it's really obvious in the residuals versus fitted values plot. So if we look at our fitted model, you can see that because we have a concave shape in our relationship, then for low values and high values of our response variable, the fitted model is tending to underestimate those values, and that's reflected in the positive residuals that we're seeing on the residuals versus fitted values plot. So low and high values are here underestimated by the model, so we get more positive than negative residuals. And in the middle of our data, the model is overestimating the values of y1, and so we tend to get negative residuals, and that's why we get this very strong curve in our residuals versus fitted values plot. If we had a relationship that was going the other way, so where the curve was more convex than concave, we'd see a curve on the residuals versus fitted values plot that was going the other way, so it would be humped rather than U-shaped. But that's what it looks like when you have curved relationships rather than straight relationships in your linear model. Once again, you can say to me, well, I can just see that in the scatter plot that I've drawn, and yes, you're right. But sometimes you can't see it, even in a scatter plot like that, and it shows up on the residuals versus fitted values plot. And sometimes when you have a complex model that you're fitting, you simply can't see it at all, but again, it shows up on the residuals versus fitted values plot. Okay, so we've gone through all of our assumptions. Some of them, or one of them, we can't check with our diagnostic plots, but the other ones we can. And then you have the question of what to do when your diagnostic plots don't make you happy and you think your model assumptions have been violated. What do you actually do? Well, the first thing to do is not to panic. Don't panic. Linear models are actually surprisingly resilient to deviations from these assumptions, particularly if you have decent sample sizes, and particularly if your design is what we call balanced. So if all your treatment groups have got reasonable sample sizes, then the linear model is actually able to take quite a lot of deviation from these assumptions and still give you essentially correct answers. So first of all, don't panic. The second thing to do is to think about what it is that you're trying to do with your linear model. Do you just want to know if explanatory variable X has an effect on response variable Y, in which case you can probably tolerate quite a lot of deviation from your assumption because you're just looking at a big qualitative answer? Or do you want to be able to accurately predict response variable Y from a whole bunch of explanatory variables that you might be throwing into some multiple regression? And if you want really accurate predictions, then you're going to have to worry more about deviations from these assumptions than you would if you're just thinking about straightforward qualitative answers. And then the third thing to think about is, well, is the problem that I've identified actually likely to affect what I'm concluding from my model? Is it, have you just got a small amount of kurtosis in your residuals, and are you looking for a qualitative answer? In which case it's probably not going to have an effect. Do you have strongly positively skewed residuals and you're looking to be able to make precise predictions? If that's the case, then you're going to have to do something about it. If you think that the problem you've identified is likely to affect your conclusions, and knowing whether it is or isn't, I'm afraid, is largely a matter of experience, then you're going to have to check that, and you've got a bunch of different options. So one thing that people do an awful lot is data transformation. So things like heteroskedasticity, non-normal errors, sometimes non-linearity, can sometimes be fixed by beating your data with some kind of transformation, square root transformation, log transformation, something called a Box-Cox transformation. All of these can make your data much better behaved and return the data to a situation where the model assumptions are no longer violated. If you do transform your data, of course, you have to remember that you're now fitting a model to transform data, and the conclusions that you draw apply initially to the transformed data rather than the untransformed data. But data transformation will often fix a lot of these problems. If you can't transform your way out of the problem, you might be able to just fit a different model. So if you have non-linearity, for example, you can fit a model that actually takes that into account in some cases. So you can fit maybe a quadratic model, which will allow you to have a certain amount of curve in your relationship. If that's not going to do the trick, you're probably going to have to use a different kind of analysis. So you might want to use something like a generalized linear model, where we take the distribution of the residuals into account, and we can fit models to data which you will never be able to transform so that the linear model would be useful. There are other things like generalized additive models that can take complex curve relationships into account. So you might try to use a different analysis. Something that you might hear people saying or read in old stats textbooks is, if you can't fix this, use a non-parametric test. It's very rare nowadays that we have to use non-parametric tests because we have such an arsenal of parametric statistical models that can take data sets that deviate from the assumptions of the linear model into account. Okay, so don't panic. Think about why you're doing the analysis. Think about whether the problem that you've identified is likely to actually be affecting your conclusions. And if it is, you've got a whole bunch of options to try and fix it. One last thing that we should mention is the other thing you can do in order to check your model assumptions. And this is running statistical tests on your data to see if they conform, to see if your data conform to the assumptions of the linear model. So there's a whole bunch of statistical tests that you can do which will tell you things about your data. So for example, you can run a Levene's test to see if your variance is homogeneous. You can run a Kolmogorov-Smirnov test to check whether your residuals are normal. And you will very often see people doing this. If you look in the published literature, the published biological literature, there are thousands and thousands of examples of people doing these statistical tests. The question is whether you should do these tests and whether you should base your analysis on the results of these tests. In order to get some insight into that, first of all, think about what a significant result tells you. So let's say you do a Levene's test and you get a significant result that tells you that the variance in your data significantly deviates from a homogeneous distribution across your data set. That tells you that you've got a significant difference from a homogeneous distribution. What it doesn't tell you is whether that difference is actually going to affect the outcome of your analysis. One thing to think about is that if you have a very large data set, you will almost always get a significant result with these kinds of tests because real data sets never conform exactly to these assumptions. If you've got a huge data set and you get a significant result on a Levene's test because you've got a very small deviation from homogeneity of variance, that deviation isn't going to affect the output of your analysis at all. So getting that significant result doesn't actually tell you anything useful. What you need to know is whether there's whether there is a large enough deviation from these assumptions to make an important difference to the outcomes of your model. And a significant result from a test like this doesn't tell you that. Second thing to think about is, what does a non-significant test result tell you? Well, it doesn't tell you that your data conform to the assumptions. Statistical significance tests don't tell you if things are the same. They can only tell you if things are different. So if you've got a small sample size, you're quite unlikely to get a significant result because your sample size is small, even though your assumptions might be quite badly violated. So once again, a non-significant result doesn't tell you anything useful, and a significant result doesn't tell you anything useful. So on that basis, I think it's reasonable to say that most statisticians would not recommend using these kinds of tests to base your analysis on. You might want to use them to give you some guidance, but you certainly shouldn't use them to base decisions without thinking very carefully about what it is they're telling you. Okay, that's enough on that. So let's just wrap this up. When you're fitting a linear model, you always need to check at least the QQ plots and the residuals versus fitted values in order to check that your residuals are behaving in the way we'd like them to behave. When you're dealing with real data, your diagnostics will never be as pretty as you would like them to be. There will always be something funky about your QQ plot or something weird about your residuals versus fitted values plot. That means that you're going to sit there scratching your head and worrying about it. The thing to do is not to lose sleep over it, but as I've said, ask whether that violation of assumptions is big enough to make a difference to your conclusions. That's largely a matter of experience. If you're not sure, then try and fix it and see if the conclusions change. And if they don't change, then you probably don't need to do that transformation. If it's not obvious in the diagnostic plots, particularly when you've got nice big sample sizes, it's probably not a problem. If you can't see it when you first look at it, it's probably not going to be a problem. And finally, once again, don't panic. The linear model is largely robust to small violations of these assumptions. So if your violations of assumptions are not really big ones, there's a fairly good chance they're not going to make any difference. Okay, thank you.